Let's start with a simple thought experiment. Imagine you are sitting on your couch, scrolling through your phone, not a single muscle moving except maybe your thumb. You might feel motionless, like a statue with Wi-Fi. But in reality, you're hurtling through space at a speed that would make even the fastest rocket look like it's stuck in traffic. The reason it doesn't feel that way is because motion, in the cosmic sense, is relative. You only feel speed when something else around you isn't moving at the same rate. On Earth, you feel a car accelerating because your body and the car are fighting to stay in sync. In space, however, everything around you is moving together in a perfectly synchronized cosmic ballet. And that makes stillness one of the greatest optical illusions the universe ever pulled off. Good evening, curious minds. I truly hope you will enjoy today's video. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift towards sleep, consider subscribing, but only if you enjoy these calm journeys through the universe. Now let's begin. The idea that we're moving through space might sound like something from a science documentary narrated by a soothing British voice, but it's also deeply personal. Every second of your life, you're part of a journey that started before you were born and will continue long after you're gone. The chair beneath you? It's part of Earth's crust, spinning and orbiting in perfect coordination. The air you breathe? It's tagging along for the ride. Even your atoms, the ones that make up your skin, hair, and bones, were forged in ancient stars that once raced through galaxies of their own. You are not just moving through space. You are space in motion. To understand why this illusion of stillness exists, we have to think about reference points. When you're on a train and another train beside you moves at the same speed, it looks like you're not moving at all. You could be gliding at 200 miles per hour, but if everything outside your window is matching your pace, your brain shrugs and says, "Seems chill." Now, apply that logic to the entire planet. Everything you see, clouds, trees, cities, oceans, is on the same cosmic train, and there's no nearby platform to remind you that you're speeding. The universe doesn't have a window view that shows motion. It's motion all the way down. But here's the twist. Even though we can't feel it, scientists can measure it. The cosmos leaves breadcrumbs, tiny clues like the way light from distant stars bends, stretches, and shifts as we move. Think of it as the universe's speed radar. When scientists analyze that light, they see patterns that reveal how fast we're really going. Spoiler alert, it's fast enough to make the word speeding sound cute. So why call it a cosmic speed trap? Because every time we think we've figured out how fast we're moving, we realize there's another layer of motion we forgot to account for. First, there's the rotation of the Earth. Then there's the orbit around the sun. Then the sun itself moving through the Milky Way. Then the Milky Way moving through the universe. It's like discovering that your treadmill is on another treadmill, which is on a spaceship, which is itself hitching a ride on a cosmic escalator. You're never actually here. You're always going. There's something profoundly humbling about that. We humans love to think of ourselves as grounded creatures. We build homes, pin maps, and draw borders, as if we can anchor ourselves to a solid, immovable point. But the universe doesn't do stationary. It's all motion, all the time. Even the atoms in your body are buzzing with restless energy, vibrating at speeds that defy the idea of stillness. The universe doesn't stop so you can check your phone notifications. It's far too busy expanding, swirling, and dragging you along for the ride. Now, before you panic about being flung through the void at unimaginable speeds, take comfort in the fact that motion is surprisingly gentle when everything is moving together. You don't feel Earth spinning because you're part of that same spin. The same goes for the orbit around the sun or the sun's path around the galaxy. Space isn't like the jerky ride of an old amusement park roller coaster. It's the smoothest cruise imaginable. The only reason you might lose your coffee is if gravity decides to get creative, and thankfully, it's been pretty consistent for a few billion years. Here's the funny part. The faster we move, the less we notice it. Motion becomes invisible when it's universal. The entire cosmos could be hurtling through some higher dimensional space, and we'd be none the wiser. That's both terrifying and kind of beautiful. It means that home isn't a place. It's a constant motion shared by everything you've ever known. So next time you look up at the stars, remember that they're not just twinkling in the sky, they're streaking through space like you are. The universe is one massive traffic jam of cosmic proportions, except no one's honking and everyone's obeying gravity's speed limit. You, me, the Earth, the sun, we're all part of an endless, invisible voyage that began at the dawn of time. You're not sitting still. You're surfing the universe. And the best part? You didn't even need a boarding pass. The Earth's spin is one of those things we take for granted, like Wi-Fi or oxygen. You never notice it, yet it's working non-stop, shaping everything from our day-night cycle to the way hurricanes twirl. It's easy to imagine the planet sitting calmly in space, but in truth, Earth is a restless dancer. Every 24 hours, she completes a perfect pirouette around her axis. And she's been doing it for billions of years without missing a beat. That's dedication. The reason Earth spins in the first place goes back to its birth. Picture a chaotic cloud of gas and dust collapsing under gravity's pull about 4.5 billion years ago. As that cosmic debris clumped together to form a new world, it conserved its angular momentum, meaning it started to spin faster, just like a figure skater pulling in their arms. That ancient motion never stopped. It's the same spin you're riding right now. So if you ever feel like your life is going in circles, well, technically it is. About one complete circle every day. But Earth doesn't spin evenly everywhere. Near the poles, the surface moves slower because you're closer to the planet's rotation axis. At the equator, though, the ground beneath your feet is zooming along at about 1,000 miles per hour. That's faster than the speed of sound. If you could somehow stand at the equator and suddenly teleport to the North Pole, you'd instantly be flung sideways like a rag doll in a physics experiment gone wrong. Thankfully, teleportation doesn't exist yet, or emergency rooms would be very busy. This wild spin has consequences you can feel, even if you don't notice them. Take the gentle bulge around Earth's middle. The centrifugal force from spinning makes the planet flatten slightly at the poles and puff out at the equator, giving it a shape that's more like a squished beach ball than a perfect sphere. It's technically called an oblate spheroid, but let's be honest, That sounds like something you'd order from a sci-fi diner. This bulge means Earth's equatorial diameter is about 27 miles wider than the pole-to-pole distance. In other words, if you stand at the equator, you're slightly farther from Earth's center than someone standing in Alaska. Congratulations, you're a tiny bit taller there. That same spin also plays a secret role in how air and water move across the planet. The Coriolis effect, caused by Earth's rotation, makes hurricanes swirl counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. It's like the planet's way of giving storms a stylish spin direction. Without it, our weather systems would look like confused clouds bumping into each other instead of the elegant spirals we see from space. Even airplane flight paths rely on this rotation. Pilots constantly adjust for the fact that Earth is moving beneath them, or they'd miss their destinations by hundreds of miles. It's cosmic multitasking at its finest. And then there's the day itself, the most familiar rhythm in human life, created entirely by Earth's spin. Morning light, noon heat, sunset calm, all of it is just a side effect of our planet turning toward and away from the sun. If the Earth suddenly stopped spinning, the consequences would be catastrophic. The atmosphere would keep moving at 1,000 miles per hour, creating winds that could rip entire continents apart. The oceans would slosh across the land, and gravity itself would shift slightly as the planet's bulge tried to even out. Basically, if the Earth hit the brakes, it would be the worst day ever, literally. But here's the real cosmic irony. The Earth's spin is slowing down, very, very slowly. Every century the day gets about 1.5 milliseconds longer. It's nothing you'd notice unless you were keeping time with an atomic clock and a lot of patience. This gradual deceleration is caused mainly by the moon's gravitational pull. As the moon tugs on our oceans, tides rise and fall, creating friction that saps a tiny bit of the planet's rotational energy. It's like the moon is applying a microscopic brake pedal. In the far future, Earth's days will stretch out to 30 hours, and our descendants, if they still have calendars, will have to rewrite what a day even means. You might wonder, if we're spinning so fast, why don't we fly off the surface like clothes in a dryer? The answer is gravity, the ultimate cosmic seatbelt. Gravity pulls you toward Earth's center with much greater force than the outward push of rotation. At the equator, the centrifugal effect does make you weigh about 0.5% less than you would at the poles, but not enough to help with your diet goals. You can't spin your way to fitness, sadly. If you could look at Earth from space, you'd see a dazzling motion picture. Clouds drifting in curved paths, oceans shimmering in the sunlight, and the whole planet twirling gracefully against the black canvas of the cosmos. That spin is what keeps our climate stable, our time measurable, and our world alive with rhythm. It defines the pace of life itself. The next time you stand outside and feel a gentle breeze, remember that you're standing on a world that refuses to stand still. You're riding the edge of a spinning giant, moving so fast that even the fastest jet couldn't keep up. Yet it feels perfectly calm. That's the magic of Earth's rotation, a dizzying, invisible dance that never lets you fall off the floor. If you have ever taken a road trip and thought driving for hours was exhausting, imagine being Earth, Our planet has been on a 4.5 billion year road trip around the sun, looping endlessly on a path so smooth and predictable that it defines our entire concept of time. One orbit equals 1 year. It's cosmic clockwork, no traffic, no gas stations, just a fiery ball of nuclear fusion at the center, and a planet full of passengers along for the ride. The orbit might seem like a perfect circle, but it's actually an ellipse, a slightly stretched oval. That shape was famously described by Johannes Kepler in the early 17th century, after he realized planets weren't following the neat circular tracks everyone assumed. In space, perfection doesn't mean symmetry, it means balance. Earth moves faster when it's closer to the sun, around early January, and slows down when it's farther away, around July. We're literally speed fluctuating through space, though no one's handing out speeding tickets for gravitational slingshots. But what's really holding us in this endless loop? Gravity, the invisible leash between Earth and the sun. It's not a constant pull like a string. It's more like a dance of mutual attraction. The sun's gravity pulls Earth inward, while Earth's momentum tries to fling it outward. Those two forces cancel just enough to keep us in stable orbit. It's a celestial tug-of-war that never ends, where both sides win because neither lets go. If gravity weakened even slightly, Earth would drift off into deep space like a runaway shopping cart. If it grew stronger, we'd spiral inward and roast long before sunscreen could evolve. To grasp the scale of this cosmic highway, picture the sun as a glowing campfire and Earth as a marshmallow roasting about 93 million miles away. Light from the sun takes about 8 minutes to reach us, which means when you look at a sunrise, you're actually seeing the sun as it was 8 minutes ago. The orbit defines not only how we experience time, but how we experience existence itself. Every change of season, every sunrise and sunset, every leap year adjustment, it's all a reflection of our perpetual motion around that central star. What makes our orbit especially fascinating is its stability. Earth's path doesn't wobble wildly or veer off course, thanks to a delicate balance maintained by the gravitational influence of other planets, especially Jupiter. Jupiter acts like the solar system's big brother, massive enough to keep things in line, but not so overbearing that it ruins the fun. Its gravity gently stabilizes Earth's orbit, preventing catastrophic shifts that could send climates swinging wildly. In short, if Jupiter didn't exist, we might have seasons that make weather apps cry. Now, this orbit isn't just about distance and speed. It's also about tilt. Earth is tilted at about 23.5 degrees relative to its orbital plane, and that little lean is what gives us seasons. As we orbit, different parts of the planet face the sun more directly, changing how much sunlight each hemisphere receives. It's cosmic choreography, summer for one side, winter for the other. Without that tilt, there would be no winter blues, no spring blossoms, no autumn colors. Just one eternal, mildly boring season everywhere. The next time you complain about snow, remember it's a side effect of the planet's elegant tilt while speeding around the sun. Even though we're traveling at 67,000 miles per hour, you feel none of it. The reason is the same as before. Everything around you is moving with you. The oceans, the atmosphere, your cat, all locked into the same orbital motion. There's no acceleration to feel, only smooth, constant velocity. It's like being in a plane flying at cruising speed. You only sense motion when it changes. If Earth suddenly stopped orbiting, we'd absolutely notice. The planet would begin falling straight toward the sun in a fiery death spiral that would make every apocalypse movie look like a nature documentary. Luckily, that's not on the schedule. There's also a poetic side to our orbit. Every year, the planet returns to the same position around the sun, but you don't. You've aged a bit. The trees have grown. Civilizations rise and fall between orbits. Earth's motion creates the rhythm of history itself. Ancient astronomers used this motion to create calendars, mark solstices, and predict eclipses long before they understood what gravity even was. They just noticed the regularity, the perfect cosmic heartbeat that measures our existence. One curious detail: our orbit isn't entirely constant. The gravitational pull of other planets, the moon, and even the sun's slight mass loss over time cause small shifts in Earth's path. These variations are part of long-term cycles known as Milankovitch cycles, which subtly alter our climate over tens of thousands of years. Ice ages, for instance, are partly influenced by how Earth's orbit and tilt change over vast time scales. In short, the planet's highway has some scenic detours built in, nothing catastrophic, just slow motion adjustments on a cosmic time scale. And if we zoom out even more, we realize that our orbital speed, impressive as it sounds, is just one small layer in a hierarchy of motion. The sun itself is moving, dragging us along through the galaxy, which is moving through the universe. But in this chapter's frame, we're focused on the local motion, the steady, graceful journey around the sun that makes our lives possible. So yes, you're flying through space at 67,000 miles per hour, and your only clue is the subtle dance of daylight and shadow. You don't feel the motion, but it defines everything you see and everything you are. Earth is the ultimate passenger, steady, loyal, and eternally circling its star. The next time you complain about your morning commute, remember, you're already taking the longest, smoothest trip imaginable, and the ticket lasts a lifetime. It's one of the great cosmic surprises. The sun, which we like to think of as the stable center of everything, is actually speeding through space like a glowing chariot with 8 planets, dozens of moons, and a few billion chunks of rock and ice clinging behind it. Picture a fireball at the front of a vast caravan with planets spinning and orbiting like decorative wheels, all zipping through an endless galactic highway. That's our solar system, an entire family of worlds on a joyride around the Milky Way. The Milky Way is enormous, so enormous that even at nearly 500,000 miles per hour, the Sun takes about 225 million years to complete a single orbit around its galactic center. That means, since the dinosaurs went extinct 66 million years ago, the Sun has only traveled about a quarter of the way around. Humanity, in the grand scheme, hasn't even been around for a single full lap. We're the cosmic equivalent of someone who just got on the ride, and is still adjusting the seatbelt. The sun's motion is not random. It follows a curved path orbiting around the galactic center, pulled by the combined gravity of everything in the Milky Way: stars, gas, dust, and a massive invisible halo of dark matter. Dark matter is the mysterious ingredient that makes up most of the galaxy's mass, though we can't see it or touch it. It's like the universe's silent partner, keeping the lights on while refusing to be interviewed. Without it, galaxies like ours wouldn't hold together. They'd simply fling themselves apart. But the sun's orbit isn't a perfect flat circle either. It bobs up and down through the galactic plane, weaving a slow, undulating path like a cosmic roller coaster. Every few dozen million years, the solar system dips above or below the galaxy's mid-plane, passing through regions with different densities of gas, dust, and radiation. Some scientists even speculate that these oscillations could subtly influence life on Earth, perhaps nudging comet clouds or altering cosmic ray exposure over long timescales. It's not a guarantee, but it does make you wonder whether our position in the galaxy has quietly shaped the story of life itself. Now imagine the solar system from the outside. The sun's gravity binds the planets in place, but as the sun moves, it drags them all along. This creates a mesmerizing visual, a spiraling trail of orbits twisting behind it, like glowing ribbons in motion. The planets aren't looping in flat circles. They're spiraling forward in three-dimensional space, following the sun's galactic trek. It's less like a merry-go-round and more like a corkscrew moving through space. You're not circling in one spot. You're surfing a continuous spiral wave through the galaxy, and the scale of that journey? Mind-bending. Our solar system's orbital radius around the Milky Way's center is about 27,000 light-years. 1 light-year is about 6 trillion miles, so multiply that by 27,000, and you get a number so big it might as well be labeled incomprehensible. The central region we're orbiting contains a supermassive black hole named Sagittarius A, weighing about 4 million times the mass of our sun. We're not in danger. It's far enough away that we'll never fall in, but it's the gravitational anchor keeping the Milky Way's stars in orbit, the cosmic equivalent of a city's downtown, glowing with raw energy. As we move, the sun carries everything in the solar system with it: planets, moons, asteroids, comets, and trillions of dust grains. The outer boundary of this moving bubble is marked by the heliosphere, a vast bubble of charged particles streaming out from the sun. This bubble acts like a protective force field, shielding the inner planets from much of the galaxy's harsh radiation. Beyond that, there's the Oort cloud, a distant shell of icy objects stretching halfway to the nearest stars. It's so loosely bound that as the sun orbits the galaxy, passing stars can occasionally tug on these icy bodies, sending some tumbling inward as long-period comets. Every once in a while, one of them streaks through our night sky, a cosmic postcard reminding us that our galactic journey is far from empty. You might think of space as empty, but the sun's galactic path takes it through a patchwork of different regions. The local interstellar cloud, for instance, is the thin wisp of gas and dust we're currently passing through. Millions of years from now, we'll drift into new territory with different densities of interstellar matter. These regions subtly shape the heliosphere, squeezing or expanding it like wind pressing against a balloon. It's the cosmic version of changing lanes on an invisible highway made of starlight and plasma. And yes, we're moving ridiculously fast, but the Milky Way is huge, and everything else is moving too. Our neighboring stars like Alpha Centauri are racing through space as well, each with its own trajectory and speed. The galaxy is more like a bustling swarm of bees than a quiet celestial painting. We just happen to be one of the bees flying in formation, guided by gravity and inertia. If you could somehow stand outside the Milky Way and watch it from a distance, you'd see hundreds of billions of stars swirling like glowing dust around a luminous core. Somewhere in one of those spiral arms, a minor one called the Orion Arm, a tiny yellow star is pulling its family of planets along, tracing a glowing arc that's as graceful as it is unstoppable. That's us. One glowing speck among hundreds of billions, part of a galaxy that itself is in motion, being tugged toward even larger cosmic structures. But for now, it's enough to know this: the ground beneath you is moving with the Earth. The Earth is orbiting the Sun, and the Sun itself is flying through the Milky Way on a journey that won't finish for another 200 million years. Your house isn't just sitting on a planet, it's bolted to a cosmic rocket, cruising through the galaxy at 500,000 miles per hour. And though you can't see the tow truck, you can feel its warmth every morning. It's the Sun, your personal chauffeur through the Milky Way. It's hard to picture something as enormous as the Milky Way moving. After all, it contains hundreds of billions of stars, countless planets, enormous clouds of gas, and mysterious swirls of dark matter. But the galaxy isn't just sitting there politely in space. It's an enormous rotating machine of gravity and motion. Every star you see in the night sky, including our Sun, is part of that motion, orbiting the galactic center like bees around a glowing hive. The Milky Way is a city of stars, and every street, bridge, and avenue is in motion, forever. The Milky Way's shape is deceptively elegant. It's a barred spiral galaxy, meaning it has a long central bar of stars from which its beautiful spiral arms unfurl like glowing ribbons. These arms are not static structures. They're more like waves in a crowd at a concert. Stars and gas move through them, but the arms themselves are density waves, where material bunches up temporarily, creating bright lanes of activity. It's like a traffic jam in space, except instead of frustrated drivers, you have newborn stars forming from collapsing clouds of hydrogen. Now, when we say the Milky Way is rotating, we mean that everything in it, stars, gas, dust, is orbiting around a common gravitational center, where a supermassive black hole lurks. That black hole, called Sagittarius A, weighs about 4 million times the mass of the Sun. But here's the weird part. Even though it's the central anchor, it doesn't act like the galaxy's engine. The Milky Way's rotation isn't powered by the black hole. It's driven by the collective gravity of everything, visible matter, dark matter, and all the stars and gas that make up its luminous spiral arms. The black hole is like a light switch in a mansion. It's crucial, but not what's holding up the building. Every star in the galaxy has its own speed and distance from the center. The Sun, for example, takes roughly 225 million years to complete one galactic orbit. Stars closer to the core move faster, while those farther out move slower. Or at least, that's what you'd expect if galaxies behaved like planets around a star. But when astronomers looked closely, they discovered something strange. The outer stars were moving too fast. According to the laws of gravity as we know them, the edges of galaxies should rotate more slowly, like the outer edge of a spinning record. Instead, the Milky Way's outer stars are zooming along nearly as fast as those near the center. This observation led to one of the biggest mysteries in modern physics: dark matter. Scientists realized there must be some invisible mass, something that doesn't emit light or radiation, adding extra gravity to the galaxy. Without it, the Milky Way would simply fly apart. Dark matter, though unseen, makes up about 85% of the galaxy's total mass. So in a way, the Milky Way isn't just a pinwheel of stars. It's a ghost ship with unseen matter steering the helm. You can't see the dark matter, but it's there, shaping every motion, every orbit, every swirl of galactic rotation. The speed of the Milky Way's spin, around 1.3 million miles per hour, is mind-boggling, but motion in space is relative. To another galaxy, we might look perfectly still, while to us, they're the ones hurtling through space. It's like being on a merry-go-round in a dark carnival, with every other carousel spinning too, and no way to tell who's really moving. The cosmic dance is dizzying and elegant, and we're one glowing note in the melody. But the Milky Way's movement isn't limited to its spin. The entire galaxy itself is drifting through space, being tugged and pulled by the gravity of other galaxies and clusters nearby. It's part of a small neighborhood called the Local Group, a cluster of more than 50 galaxies, including our nearest major neighbor, the Andromeda Galaxy. Andromeda is roughly the same size as the Milky Way and is heading toward us at about 250,000 miles per hour. In about 4 billion years, the two galaxies will collide and merge into one giant elliptical galaxy. Don't worry, it won't be as violent as it sounds. The stars are so far apart that very few will actually hit each other. It'll be more of a graceful interstellar tango than a demolition derby. Inside the Milky Way, motion isn't uniform. Some stars orbit calmly. Others follow tilted or looping paths, relics of smaller galaxies that were swallowed long ago. Yes, the Milky Way is a cosmic cannibal. It has consumed many smaller galaxies throughout its life. You can still see the evidence in long, faint streams of stars stretching across the sky, the galactic equivalent of crumbs left behind after a meal. Over billions of years, the Milky Way has grown not just by forming new stars, but by stealing them from its neighbors. It's the ultimate celestial recycler. And let's not forget the speed at which our galaxy's outermost regions move. Clouds of gas and star clusters at the edge of the Milky Way are orbiting at hundreds of thousands of miles per hour. Even the tiny dwarf galaxies that orbit us, like the Magellanic Clouds, are caught in this gravitational whirlwind, slowly being stretched and reshaped by our galaxy's pull. So yes, the Milky Way is rotating at blistering speed. But because everything inside it, every star, every atom, every dust grain, is moving with it, you feel nothing. You are part of the spin. The galaxy doesn't roar or hum. It moves in silence, vast and serene. If galaxies did have roller coasters, the Milky Ways would be the deluxe model, massive, glittering, and endlessly looping. We're strapped in, orbiting a black hole, riding waves of dark matter, drifting through starlight and ancient dust. And as we spin, we carry with us not just our solar system, but the story of everything that ever lived and will live. The galaxy moves, and we move with it, silent passengers on a ride that has no end and no brakes, only the soft, eternal pull of gravity guiding us through the dark. The Milky Way may seem enormous, and it is, but in cosmic terms, even galaxies need company. We're not drifting alone through the dark. We belong to a small but lively neighborhood of galaxies called the local group. This celestial community stretches across about 10 million light years and contains more than 50 known galaxies, all bound together by gravity in a slow, swirling gravitational waltz. It's not exactly the bustling chaos of a city, more like a spaced-out town where the neighbors are far apart, but their gravitational gossip still shapes everyone's motion. At the center of this cosmic social circle sit the two big stars of the show, our Milky Way and the Andromeda Galaxy. These are the local giants, each containing hundreds of billions of stars. Between them lies a gravitational tension so strong that the two are slowly drawing closer together, an invisible dance destined to end in a galactic merger. But more on that soon. For now, picture these two massive galaxies like slow dancing partners moving toward each other across a ballroom the size of a galaxy cluster, while dozens of smaller galaxies twirl and drift around them like backup dancers. Surrounding the Milky Way are several smaller satellite galaxies, including the Magellanic Clouds, two irregular blobs of stars visible from the southern hemisphere. They're like cosmic sidekicks, orbiting our galaxy, while slowly being stretched and distorted by its gravity. Over time, these smaller galaxies will likely be absorbed, their stars folded into the Milky Way's disk like sugar dissolving in tea. Our galaxy is polite, but it's also a little bit of a gravitational glutton. Andromeda has its own entourage too, dozens of dwarf galaxies, many of which are so faint that astronomers only discovered them in the past few decades. Most of these tiny galaxies are dominated by dark matter, with just a sprinkling of visible stars. They're the wallflowers of the galactic dance floor, quiet, ghostly, and easily overlooked, but they play an important role in shaping the local group's structure. Each one exerts its own small tug on the gravitational fabric of space, influencing how the bigger galaxies move. Now, here's where it gets truly fascinating. The Milky Way and Andromeda are heading toward each other at about 250,000 miles per hour. It sounds fast, but in the grand ballet of galaxies, that's practically slow motion. The two won't meet for about 4 billion years, and when they do, it won't be a fiery crash. The distances between stars are so vast that even during the merger, most stars will simply pass by one another like polite commuters, avoiding eye contact. Instead of collisions, the event will be defined by gravitational reshaping, arms of stars stretching, bending, and merging into new formations. The final product will be an entirely new galaxy, likely an enormous elliptical one, with a name astronomers have already picked out, Milky Way. Because of course they did. The local group is not just about the Milky Way and Andromeda, though. It also includes the Triangulum galaxy, a smaller but vibrant spiral with a few billion stars of its own. Triangulum may be the third wheel in the Milky Way-Andromeda relationship, close enough to feel the pull, but not big enough to dominate the conversation. It might one day join the merger party or continue orbiting the combined galaxy as a long-term companion. Either way, it's already gravitationally linked to Andromeda, suggesting these galaxies have been neighbors and dance partners for quite some time. The local group is held together by gravity, but it's not collapsing. In fact, the galaxies inside it are moving in a kind of balanced harmony. Gravity pulls them inward, but the expansion of the universe, the stretching of space itself, pulls everything outward. On small scales like the local group, gravity wins, holding the family together. On larger scales, cosmic expansion dominates, pushing distant galaxies farther and farther away. Think of it like a neighborhood that stays close-knit, even as the wider universe moves to the suburbs. If you could watch the local group in time-lapse over billions of years, it would look like a delicate, shimmering dance. Galaxies drift closer, merge, reshape, and settle into new forms. Streams of stars stretch between them, remnants of past collisions. The smaller galaxies get consumed, while the larger ones grow brighter and more massive. It's the slowest, grandest choreography imaginable. An interstellar ballet where every movement takes millions of years and every performer is made of stars. And yet, this entire cluster of galaxies isn't sitting still. The local group itself is moving through space, drawn toward a larger region of gravitational attraction known as the Virgo cluster. It's as if the whole dance floor is sliding across the room while the dancers continue spinning in sync. From our perspective, that movement is almost impossible to sense, but astronomers can detect it by observing the light from distant galaxies. Subtle shifts in wavelength, tiny red and blue tints, reveal the speed and direction of our galactic neighborhood's journey. It's the universe's version of traffic data, only measured in millions of light years. The local group's quiet harmony is a rare pocket of stability in an otherwise chaotic cosmos. Beyond its borders, galaxies race apart at increasing speeds as the universe expands. Inside, however, gravity maintains its grip, preserving this small family of galaxies amid the cosmic drift. It's comforting in a way. Amid the infinite vastness, we still belong somewhere. We have cosmic neighbors. So when you look up at the night sky, remember that every point of light you see belongs to this local family. The Milky Way, Andromeda, Triangulum, and all their companions are moving together through the universe like an ancient caravan, bound by gravity, shaped by time, and destined to merge, swirl, and evolve into something entirely new. It's the ultimate slow dance. 3 trillion suns, dozens of galaxies, and one unending beat of cosmic rhythm that keeps them all in motion. Just when you think you've got the universe figured out, planets orbit stars, stars orbit galaxies, galaxies orbit, well, nothing really. You find out there's something even bigger pulling the strings. The Great Attractor is one of those cosmic riddles that make scientists squint at their data and whisper, "Wait, what?" Because according to the evidence, every galaxy in our neighborhood, including the Milky Way, Andromeda, and everything in the local group, is being drawn toward an unseen gravitational center somewhere deep in space. And not just drifting a little bit either. We're moving toward it at nearly 400 miles per second. That's over 1,000,000 miles per hour, which is fast enough to cross the continental United States in about 10 seconds. So Deeb, what exactly is this invisible magnet in the sky that has entire galaxy clusters migrating toward it like cosmic moths to a flame? To answer that, we need to zoom out a lot. Our local group is part of a much larger collection called the Laniakea Supercluster, a massive region of space spanning more than 500 million light-years. It contains about 100,000 galaxies, all loosely connected by gravity. Picture a sprawling web of galaxies flowing like rivers through space, converging towards certain dense regions. The Great Attractor sits near the heart of that gravitational basin, warping the cosmic landscape around it. But here's the kicker. We can't actually see it. The Great Attractor lies in a region of the sky known as the Zone of Avoidance, a part of the cosmos obscured by our own Milky Way. The dense clouds of dust and gas in our galactic plane block visible light from reaching us, hiding whatever lies beyond. It's like trying to map a city skyline while staring through a thick fog bank. We know something massive is there because of how it pulls on nearby galaxies, but the object itself remains stubbornly cloaked. Astronomers first discovered its presence in the late 20th century while studying the motion of galaxies. They expected galaxies to move in relatively predictable ways based on the universe's expansion. But when they looked closely, they found that entire swaths of galaxies were drifting toward one direction in space, deviating from the expected flow. It was as if something enormous, something gravitationally powerful, was reeling them in. This invisible mass was dubbed the Great Attractor, and it immediately joined the ranks of cosmic enigmas alongside dark matter and black holes. Early estimates suggested that the Great Attractor might be a gargantuan cluster of galaxies, perhaps containing hundreds of trillions of suns worth of mass. But later studies revealed that it's likely part of an even larger structure. The Norma Cluster, also known as Able 3627, embedded within a titanic supercluster complex. The gravitational influence of this region extends across hundreds of millions of light-years, shaping the flow of galaxies on a truly intergalactic scale. It's not so much a single object as it is a gravitational sinkhole in the fabric of the universe, a region where the mass distribution is so dense that entire galactic superclusters are sliding toward it like rain into a cosmic drain. But just when astronomers thought they'd mapped the culprit, things got stranger. Observations revealed that the Great Attractor isn't the final destination, it's more like a waypoint. Beyond it lies an even larger gravitational feature called the Shapley Supercluster, an immense concentration of galaxies so massive that it might be the true center of pull in our region of the universe. In other words, the great attractor might not be great enough. It could just be part of a bigger, more mysterious structure pulling us in. It's the cosmic equivalent of discovering the light at the end of the tunnel is just the hallway leading to a bigger tunnel. So, what does all this mean for us? Well, it's a reminder that the universe doesn't have a fixed frame of reference. We aren't just sitting in a galaxy that's spinning, orbiting, and drifting. We're also sliding through a vast gravitational landscape shaped by unseen masses and invisible structures. Even at the largest scales imaginable, the universe has currents and eddies, like a cosmic ocean where galaxies are the ships and gravity is the tide. Some scientists think the great attractor and the vast flows of galaxies it controls can tell us something profound about the universe's structure. It's evidence that matter in the cosmos is not evenly spread out, but forms a cosmic web with filaments of galaxies stretching between vast voids of empty space. The great attractor sits along one of these filaments, serving as a junction where cosmic rivers of matter converge. If the universe were a spider web, this would be one of the knots holding the strands together, and yet, despite all our technology, we're still peering through the cosmic fog, trying to understand what lies beyond. Future telescopes that can see through the dust, using infrared or radio wavelengths, may one day reveal the great attractor's true form. Maybe it's an enormous cluster of galaxies. Maybe it's something even more exotic, like a concentration of dark matter so vast that it bends space itself. Until then, it remains a gravitational whisper from the deep universe, a silent, invisible force guiding our entire galactic neighborhood toward a future we can't yet see. If you ever feel like you're not going anywhere in life, remember, you, your planet, your star, your galaxy, everything is being pulled toward an unseen destination at unimaginable speed. The great attractor is proof that even in the stillness of the night sky, motion and mystery are everywhere. Somewhere out there across hundreds of millions of light years, the universe is tugging on us, quietly insisting that we keep moving toward the unknown. Picture this: nearly 14 billion years ago, the universe lit up with the most spectacular explosion imaginable, the Big Bang. In that instant, all space, time, and matter burst into existence. For the first few 100,000 years, everything was a blinding fog of heat and light, a swirling soup of particles so dense that photons, tiny packets of light, couldn't travel freely. But as the universe expanded and cooled, that fog finally thinned, and light broke free to travel unimpeded for the first time. That ancient light is still moving through space today, washing over us constantly. It's stretched into long microwave wavelengths by billions of years of cosmic expansion, and we call it the cosmic microwave background, or CMB. You can think of the CMB as the oldest photograph ever taken, the baby picture of the universe. It captures the moment the cosmos transitioned from opaque to transparent, about 380,000 years after the Big Bang. If you could somehow see it with your eyes, the entire sky would glow faintly in every direction, a uniform background of microwave radiation. It's the afterglow of creation itself, filling every corner of space like a silent hum that never stops. Now, this cosmic afterglow isn't just a pretty relic. It's a reference frame. It provides scientists with a kind of universal backdrop against which motion can be measured. Imagine floating in deep space with no nearby stars, planets, or galaxies. How would you know if you were moving? Without a point of reference, motion becomes meaningless. But the CMB gives us that reference. It's everywhere, equally spread in all directions, the same no matter where you are in the universe. In theory, if you were truly stationary relative to the cosmos, you'd see that faint microwave glow looking identical in every direction. But that's not what we see. When scientists first measured the CMB with precise instruments, they noticed something odd. It wasn't perfectly uniform. The radiation was slightly stronger, hotter in temperature terms, in one direction of the sky, and slightly weaker, colder, in the opposite direction. This wasn't random noise. It was the universe's way of saying, hey, you're moving. That subtle temperature difference is called the dipole anisotropy, and it's the cosmic equivalent of the Doppler effect, the same principle that makes a siren sound higher pitched as it approaches and lower as it moves away. What this means is that Earth, the Sun, and the entire Milky Way are moving through space relative to the CMB. The direction of motion? Roughly toward the constellation Leo. The speed? About 1.3 million miles per hour. That's over 500 kilometers per second, fast enough to reach the moon in under half an hour if we were driving straight there. What's incredible is how precisely scientists can measure this motion using the faintest signal imaginable. The difference in temperature between the hot and cold sides of the sky is just a few thousandths of a degree. But that tiny shift encodes enormous information about our cosmic motion. It tells us not only how fast we're moving, but also in what direction, allowing scientists to anchor our entire cosmic neighborhood, the local group, the Milky Way, the Sun, Earth, and everything on it, within a universal coordinate system. For the first time, we can say how fast we're traveling, not just relative to nearby stars, but relative to the universe itself. And here's where it gets mind-bending. The CMB is the same everywhere, no matter where you go. If you were on a planet halfway across the universe, you'd still see it surrounding you, almost identical to what we see here. It's not centered around Earth. It's centered around existence itself. This is the closest thing we have to an absolute reference frame, a cosmic background that ties the entire universe together in one grand, measurable motion. The CMB also tells us about the universe's structure on the largest scales. Those tiny variations in temperature, barely a few microdegrees, are the imprints of the very first ripples in the fabric of space-time. They're the seeds from which galaxies eventually grew. The slightly denser regions of that early universe had a bit more gravity, pulling in more matter over billions of years to form stars, planets, and everything else. Every galaxy you've ever seen, including our own, owes its existence to those subtle variations frozen in the CMB. It's not just a speedometer, it's a cosmic origin story written in light. To study it, scientists use satellites like COBE, WMAP, and Planck, which have mapped the CMB with astonishing precision. These maps reveal a universe that's both astonishingly uniform and delicately imperfect, sprinkled with tiny temperature fluctuations that trace the earliest structures of cosmic evolution. The CMB is not just background noise, it's a living fossil, older than any star, older than any atom we know. But perhaps the most profound part of all this is philosophical. The CMB gives us perspective. It shows that motion is everywhere and nowhere at once, that even as we hurtle through the universe at 1,000,000 miles per hour, there's no central point, no cosmic headquarters we're moving away from or toward. The universe doesn't have a preferred location. It's expanding equally in all directions. The CMB is not a wall or a finish line. It's the echo of a beginning that's still unfolding. When you tune an old analog television between channels and see static, about 1% of that fuzz comes from the CMB, the leftover light from the dawn of time. That means every time someone stared into static, whether they knew it or not, they were glimpsing the oldest light in the universe, the afterglow of everything. So the next time you feel still, remember, the cosmos says otherwise. You're flying through space, through history, through the very echo of creation itself. The universe left us a speedometer made of ancient light, and according to it, we're cruising through eternity at over 1,000,000 miles an hour, all without spilling a drop of coffee. It's one of those things that feels impossible the first time you think about it. We're spinning, orbiting, and hurtling through space at speeds that make even light blush, and yet we feel nothing. No rush of wind in our faces, no sensation of acceleration, no tug in any direction. The universe is pulling off the greatest motion illusion ever conceived. If the Earth is doing over 1,000 miles an hour just by spinning, and over 1,000,000 by galactic standards, why does it feel like we're sitting perfectly still? The answer lies in one of the most elegant ideas in all of physics: relative motion. Motion by itself doesn't create sensation. It's changes in motion that do. You feel acceleration, not constant velocity. When you're in a car moving smoothly down a highway, you don't feel the motion at all. Everything inside moves with you. But the second the driver brakes or turns sharply, you're thrown forward or sideways because your body was still obeying the old direction. The universe works exactly the same way. The reason you don't feel Earth's incredible speeds is because those speeds aren't changing in any dramatic way. We're in perfect, steady motion, coasting through space with all our surroundings moving in sync. This synchronized movement is what physicists call an inertial frame of reference. Essentially, an inertial frame is a region of space where everything shares the same motion, making that motion invisible from the inside. On Earth, you, your house, the oceans, and the atmosphere are all part of the same inertial frame. You don't fly off into space because gravity glues you to the surface, and the air moves with the planet. So you're cocooned in a stable, balanced environment. You might as well be inside a spaceship moving at constant speed. Without acceleration, you wouldn't even know you were moving. To feel motion, something has to change. That's why astronauts aboard the International Space Station float weightlessly. They're orbiting Earth at nearly 18,000 miles per hour, but so is the station itself. Everything inside it, including the astronauts, is falling around Earth at the same rate, so there's no relative motion between them. They feel nothing because they're all in free fall together. Gravity keeps them in orbit. Physics keeps them balanced. It's motion disguised as stillness. The same principle applies on every scale. The Earth moves around the sun, but the oceans, mountains, clouds, and you all share that motion. The solar system moves through the galaxy, but the sun, planets, and all their moons are caught in the same gravitational dance. It's motion without contrast. Imagine running on a treadmill while everything, the air, the treadmill, even the room, runs at the same speed beside you. You could be sprinting at top speed, but to you everything appears frozen. That's what the universe is doing. But what's truly remarkable is that our bodies evolved in this constant motion. To us, it feels like stillness, because we've never known anything else. The spinning of the planet, the orbital journey around the sun, the galactic drift. These have been constants for every organism that ever lived. There's no evolutionary reason for us to sense them. Our balance systems are designed to notice small local accelerations, like tripping on a rock or riding an elevator, not the serene, unchanging momentum of a planet gliding through space. The vestibular system in your inner ear can detect motion only when forces change direction or speed. Earth's motion through the cosmos is so steady that your body might as well be asleep to it. Even gravity, that ever-present tug we feel, isn't fighting our motion, it's guiding it. Gravity doesn't pin us to Earth while the planet moves beneath our feet. It moves with us. It's not like being strapped to a ride. It's more like being part of the ride's structure itself. We're woven into the same gravitational fabric that moves the planet, which means we're passengers and vehicle at once. There's also the matter of scale. Space is so vast that even at mind-boggling speeds, everything around us appears static. Imagine driving through a city made entirely of mountains, hundreds of miles tall. Even at highway speed, the scenery would look like it's barely moving. Our motion through the galaxy is so immense in scale that the distances make our speed effectively invisible. The stars we see tonight look the same as they did when the first humans looked up tens of thousands of years ago. Not because nothing's moving, but because everything is moving together. This idea that motion is relative was one of the insights that inspired Einstein's theory of relativity. He realized there's no such thing as absolute rest. Everything is moving relative to something else, and you can't really say one object is truly still. From your perspective, Earth seems stationary and the stars move. From the sun's perspective, Earth is racing around it. From the galaxy's perspective, both are being dragged along by larger structures. It's motion all the way up and all the way down. Stillness is just a matter of perspective. Now, if the Earth were to suddenly change its speed or direction, say, if it stopped spinning or its orbit shifted, you'd feel it instantly and unpleasantly. In fact, if Earth stopped rotating even for a moment, everything not bolted to bedrock would continue moving at 1,000 miles per hour. That includes you, your house, the oceans, and every last molecule of air. It's not the motion that's dangerous. It's the change in motion that does the damage. Thankfully, the cosmos is far too graceful for such sudden jolts. So the next time you're lying still and staring at the ceiling, convinced nothing's happening, remember this: you're traveling faster than any jet, on a planet spinning faster than any bullet, inside a galaxy soaring faster than any imagination can truly grasp, and yet you feel none of it. The air in your lungs, the floor beneath your feet, the coffee in your cup, all part of one perfect, synchronized motion. Cosmic teamwork so seamless it feels like peace. Stillness, it turns out, is not the absence of motion, it's harmony within it. We humans like to orient ourselves. We label things north and south, up and down, left and right, because our planet gives us a convenient reference point, a spinning globe with gravity politely telling us which way is down. But step outside that blue marble, and suddenly those directions evaporate. In space, there's no universal up, there's no down, there isn't even a fixed sideways. Every direction is just direction. The universe doesn't come with a compass. It's more like an infinite ocean with no top, no bottom, and no shoreline. If you've ever seen astronauts floating in the International Space Station, spinning lazily and upside down, or is it right side up, you've already seen this principle in action. Their up depends entirely on which way they're facing and which wall of the station they've decided to call the floor that day. The concept of up and down exists only when gravity gives you a hint about which way to fall. Without gravity tugging on you, there's no preferred direction. You could just as easily declare the ceiling the floor, and no one could argue with you. Our sense of direction is a deeply earthly habit. On our planet, gravity provides a clear bias. It points us toward the center of Earth. That's why down feels universal. But in space, gravity doesn't point one way. It points toward every mass. If you were floating between Earth and the Moon, both would be tugging on you, and your sense of direction would become completely confused. Pointing down would just mean toward the nearest strong gravitational pull, which could change every few moments depending on where you are. Up would be whatever direction gravity isn't. Space doesn't care about our instincts for orientation. You can rotate your spaceship however you want. And as long as nothing else is nearby to use as a visual guide, you wouldn't know which way you're facing. There's no universal grid out there, no galactic floor tiles neatly labeling the X, Y, and Z axes. The only way to define up in space is to arbitrarily pick something, say a distant star, and declare, "That way." Congratulations, you've just created your own coordinate system. It's as valid as anyone else's. The lack of absolute direction isn't just a fun quirk. It's a fundamental truth of physics. Einstein's theory of relativity showed that there's no universal frame of reference in the universe. Every object moves relative to something else, and no perspective is more correct than another. To an astronaut orbiting Earth, the planet spins beneath them. To someone standing on Earth, the astronaut is the one circling overhead. Both views are right. Both are equally valid. The cosmos doesn't pick favorites. In a way, space's directionlessness is wonderfully democratic. Every traveler defines their own up. The Milky Way spins one way, Andromeda spins another, and neither of them is upside down, Even our solar system's planets tilt and wobble at strange angles. Uranus, for instance, spins on its side like a sleepy marble that fell over, while Venus rotates backward compared to almost every other planet. If space had a rule book, these worlds would be breaking it. But there isn't one, and that's the beauty of it. The universe is a chaos of orientations, and everything's fine with that. You might wonder, though, if space has no up or down, how do astronomers describe where things are? The trick lies in relativity and agreement. Scientists use coordinate systems tied to particular objects, like Earth or the Milky Way. For instance, we map stars using celestial coordinates, declination and right ascension based on Earth's own equator projected onto the sky. But that's purely a convenience, not a cosmic truth. Move to another galaxy, and you'd have to invent an entirely new map with its own definition of north. Directions in space are local languages, not universal laws. Even the idea of north in space is more cultural than physical. On Earth, our north is defined by the planet's rotation and magnetic field, which points roughly toward the North Pole. Extend that concept into space, and you get the North Galactic Pole, an imaginary direction perpendicular to the plane of the Milky Way. But again, it's a human construct, a label we stick onto infinity to make it feel a little more manageable. The universe doesn't recognize your compass app. The consequences of this cosmic neutrality go beyond disorientation. It changes how we think about motion itself. Because there's no fixed direction. There's also no absolute movement. You can't say something is truly moving or truly still because there's no backdrop to compare it to. Everything is relative to something else. It's like being on a train in the dark next to another train moving at the same speed. Without looking outside, you'd never know if you were both moving or perfectly still. Space is like that. Except with galaxies instead of trains and a lot fewer snacks. For astronauts, this lack of direction can mess with the brain's wiring. The human vestibular system, built to interpret gravity's constant tug, becomes confused in microgravity. Up and down lose meaning, and your inner ear stops sending reliable signals. That's why astronauts often feel disoriented during their first days in orbit. Their eyes see one thing, the inside of a spacecraft, but their bodies sense another. Over time, the brain adapts, rewiring itself to live without a preferred direction. Down becomes whatever surface your feet happen to touch at the moment. Yet the more you think about it, the more liberating this becomes. The universe doesn't impose directions, it offers perspectives. Up and down are inventions born from local circumstances, not cosmic law. If you could float freely in intergalactic space, there'd be no right way to orient yourself. You could spin end over end and call that north, and the universe would simply shrug. The truth is, we crave order in the face of chaos. We draw maps on an infinite canvas, invent directions for comfort, and build meaning where the universe offers none. But in that act of labeling, we also reveal something profound. We are the only species, as far as we know, that tries to make sense of direction in a directionless universe. So next time you look up at the night sky, remember, up is just a word. You're not looking above you, you're looking out. Every direction you can point is equally valid, equally infinite, equally yours. The cosmos doesn't have a North Star. It just has stars. And they're all waiting, indifferent but luminous, in every possible direction you choose to call up. If there's one concept that forever changed how humans think about motion, it's Einstein's theory of relativity. Before Einstein, scientists believed in something called absolute space, the idea that there was a cosmic stage where everything played out, and movement could be measured against that stage. It was like imagining the universe as a giant theater with stars and planets performing on a fixed floor. But Einstein walked in, tore up the floorboards, and said, "There is no stage. There's only the dance." Relativity flipped the idea of motion upside down. It said that there's no universal rest or speed, only how things move relative to each other. You can't say an object is absolutely still. You can only say it's still compared to something else. This might sound philosophical, but it's pure physics. If you're sitting in a car cruising smoothly down a highway, you might say you're not moving. From your perspective, your coffee, your steering wheel, and your phone are all stationary. But step outside the car, and an observer on the sidewalk would disagree. You're speeding past them at 70 miles per hour. Both of you are correct. Each is describing motion from their own frame of reference. Now take that idea and stretch it across the universe. You're sitting here, feeling perfectly motionless, but relative to the sun, you're spinning with Earth at about 1,000 miles per hour. Relative to the galaxy, you're orbiting at over 500,000. Relative to the cosmic microwave background, you're hurtling along at more than 1,000,000 miles per hour. And yet, from your own point of view, you haven't moved an inch. The universe doesn't care who's right, because there is no right, only relationships between moving things. Einstein's great leap was realizing that this relativity of motion doesn't just apply to speed, it also reshapes space and time themselves. The faster you move, the more your experience of both begins to warp. Time slows down, distances contract. Clocks tick differently for people moving at different speeds. It's not an illusion. It's how the universe keeps its internal math consistent. Imagine two astronauts. One stays on Earth while the other zooms through space in a high-speed ship nearing the speed of light. When the traveling astronaut returns, they'll have aged less than the one who stayed behind. This isn't science fiction. It's been tested. Atomic clocks flown around the world on airplanes tick slightly slower than identical clocks left on the ground. The effect is minuscule at normal speeds, but as you approach light speed, it becomes dramatic. Time itself bends to ensure that the laws of physics remain the same for everyone, no matter how fast they're moving. This concept is called time dilation, and it's one of relativity's strangest gifts. It means there's no universal now. What you call the present might already be someone else's past, depending on where they are and how fast they're going. Every observer carries their own version of reality, stitched together by light signals and motion. If you and an alien on the other side of the galaxy tried to agree on what's happening right now, you couldn't, because now isn't the same everywhere. The universe doesn't synchronize watches. It lets each observer live in their own personal slice of time. And that's not even the weirdest part. Space and time aren't separate things at all. They're fused into a single entity called space-time. Think of space-time as a giant, flexible fabric that everything in the universe sits on. Mass and energy warp this fabric, creating what we perceive as gravity. A star bends space-time so much that planets orbit it. Light itself curves as it passes by. There's no invisible force pulling objects together, just geometry playing tricks on motion. Einstein replaced Newton's force of gravity with the idea that objects are simply following the curves of space-time, like marbles rolling along a warped rubber sheet. Relativity also redefines what speed means. The speed of light, about 186,000 miles per second, isn't just a fast number. It's a universal speed limit. Nothing can move faster than light because light's speed is woven into the structure of space-time itself. It's the cosmic conversion rate between distance and time. Go faster, and the equations demand that time itself must slow down to compensate. Try to hit the speed of light, and time for you would stop altogether. It's like the universe saying, "Nice try, but no shortcuts." You might wonder, if motion and time are so flexible, how do we ever measure anything at all? The trick is that physics stays consistent within each observer's own frame. If you're on a spaceship moving near light speed, your clock still ticks normally for you. Your coffee still pours the same way. It's only when you compare your reality to someone else's that the weirdness shows up. Relativity doesn't make the universe chaotic. It keeps it fair. Everyone gets their own version of reality, but the rules are the same in all of them. Einstein's insight transformed more than physics. It transformed perspective. It revealed that the universe isn't a rigid stage, but a living, elastic arena where motion, time, and space are all negotiable. There's no cosmic referee declaring who's stationary and who's speeding. Every observer has their own truth. Even the idea of simultaneity, the notion that two events happen at the same time, depends on where you're standing and how fast you're moving. The cosmos doesn't deal in absolutes. It deals in relationships. So when you think about your place in the universe, remember this: you're not standing still in any meaningful sense. To one observer, you're racing through space. To another, you're motionless. Both are correct. The universe is a hall of mirrors where motion, time, and reality shift depending on who's looking. Einstein didn't just change how we measure speed. He changed what it means to move at all. Relativity reminds us that the universe isn't bound by human common sense. It doesn't have a single truth, it has a million truths, all valid, all coexisting. From one vantage point, you're a blur of motion. From another, you're perfectly still. In a way, we're all right. And that's the weird, wonderful beauty of physics. Time feels like the one thing that should be stable. We live our lives by it, trust it to move forward,
and rely on it to keep everything in order. But the universe, in its usual trickster fashion, doesn't see time as something rigid or universal. It treats it like a flexible thread, stretching and squeezing it depending on how fast you move or how close you are to massive objects. Einstein revealed this strange truth over a century ago, and ever since, we've been learning that time isn't the ticking of a universal clock. It's a deeply personal experience. Let's start simple. Imagine two friends, both with identical watches. One stays on Earth. The other boards a spaceship and takes a joyride around the galaxy at nearly the speed of light. When they reunite, the traveler's watch will show less time has passed than the one left behind. The space traveler has literally aged less. They haven't just missed a few text messages. They've lived through fewer seconds of existence. This is time dilation, one of the most profound consequences of relativity. The faster you move through space, the slower you move through time. That might sound like a science fiction plot, but it's measurable, repeatable science. Even on Earth, time dilation is real. Satellites orbiting our planet experience time differently from clocks on the ground. Because they're moving fast and are farther from Earth's gravity, their onboard clocks tick slightly faster than ours, by a few billionths of a second each day. That may seem laughably small, but it's enough to throw off the entire global positioning system. GPS satellites constantly correct for these effects, so your phone knows whether you're at a coffee shop or 3 blocks away in the river. Without accounting for relativity, your map would be about as accurate as a drunken pirate's treasure chart. So what's really happening here? The key idea is that space and time are part of a single fabric called space-time. When you move faster through space, nature automatically slows your passage through time to keep the total pace, through both space and time, consistent. You can think of it like a trade-off. Move more through one dimension, move less through the other. The universe keeps the sum of your motion constant, as if enforcing some cosmic budget. You can spend your motion on distance or on time, but not both at once. Now, time dilation isn't limited to motion. Gravity also plays a role, bending time itself. The stronger the gravity, the slower time passes. This means that time actually ticks a little slower at sea level than it does on a mountaintop. You, reading this right now, are aging ever so slightly faster than someone sitting in a submarine under the ocean. The difference is microscopic, fractions of a nanosecond, but it's real. Experiments using ultra-precise atomic clocks have confirmed it again and again. Gravity literally stretches and compresses time like a rubber band, and the deeper you are in a gravitational well, the slower your clock runs. In space, this creates some wild effects. Near a black hole, where gravity becomes extreme, time slows to a crawl. To an outside observer, someone approaching the black hole's edge would appear to move slower and slower until they seemed frozen in place. From the traveler's perspective, however, time would feel normal. They wouldn't notice anything unusual. That's the cruel paradox of relativity. Both perspectives are correct. The universe doesn't pick one reality. It keeps both. This relationship between motion, gravity, and time isn't just theoretical. It has practical implications for the future of space travel.
If humans ever build ships capable of near light speeds, their passengers will experience time dramatically differently from people back home. A few years aboard a fast-moving spacecraft could correspond to decades or even centuries on Earth. It's called the twin paradox. One twin takes a relativistic joyride, the other stays home, and when they meet again, they're different ages. The paradox isn't a contradiction, it's the logical result of how space-time works. But here's the poetic side of it. Time dilation means every journey through the universe is also a journey through time. You can never move without bending the flow of seconds, however slightly. Every flight, every orbit, every step shifts your relationship with time. You've already been a time traveler without realizing it. When you fly on an airplane, your watch ticks a tiny bit slower than those of the people you left behind on the ground. By the time you land, you're a few trillionths of a second younger. Congratulations, you've time traveled, and you didn't even have to invent a machine. The deeper implication is that now is not universal. There is no single cosmic moment shared by everyone, everywhere. Time is local, custom-tailored to each observer's experience of motion and gravity. It's as if the universe hands out personal timelines to everyone and says, "Don't worry, it'll all make sense from your point of view." What we call the flow of time is really our movement through the fabric of space-time, a one-way path that can stretch, warp, or twist, depending on how we travel. Einstein's insight also redefines what aging means. It's not a biological inevitability, it's a space-time process. Your body's atoms, your heartbeat, your thoughts, they all unfold within your local slice of time, ticking at the rate defined by your motion and gravity. In a sense, every living being experiences their own tempo of existence. The universe doesn't play one song, it lets every particle have its own rhythm. And though the effects are tiny in our daily lives, they whisper a deep truth. Time is not the same everywhere. It's personal, elastic, and malleable. We live in a cosmos where moving faster can stretch seconds, where gravity itself can bend the clock, and where the present is just one perspective among many. So the next time you check your watch, realize it's not just telling you time. It's measuring your journey through space-time. Every tick is a reflection of your speed, your gravity, your path through the universe. Time isn't something that happens to you, it's something you do. You're sculpting it every moment simply by existing, by moving, by being part of a cosmos where time and motion are forever entangled. In short, time is not free. It's the hidden cost of motion. The faster you go, the slower it flows. The universe keeps its balance, even if it means your watch disagrees with everyone else's. Right now, our species is blessed or cursed, depending on your stomach, with a nervous system that politely ignores the fact that we're careening through space at speeds that make race cars look like lazy turtles. The human body evolved to handle the speed of a sprinting cheetah, not the rotational velocity of a planet or the orbital momentum of a star system. We only detect acceleration, those changes in motion that make your inner ear wobble. But imagine if evolution had decided differently, and we could feel absolute motion. The universe would suddenly feel like an amusement park designed by a cosmic prankster. Let's start with the simplest spin, Earth's rotation. Right now, you're spinning at roughly 1,000 miles per hour at the equator. But you don't feel it. If you could, every moment would come with a constant sideways tug. You'd feel a subtle pressure urging you toward the east, a whisper of motion pushing against your body like a never-ending wind. Standing still would feel like balancing on a perpetually turning turntable. Oceans would roar louder, air currents would be thunderous, and sleep would probably be an extreme sport. Now add Earth's orbit around the Sun, 67,000 miles per hour. If your body could feel that, you'd sense a continuous forward rush, as if you were strapped to a high-speed train with no brakes and no track. You'd look out at the stars, and they wouldn't seem like tranquil pinpricks. They'd streak and blur, stretching into luminous trails. The night sky would never be still again. It would be a motion painting in perpetual flux. Of course, our solar system isn't just orbiting the sun. It's being dragged along by the sun as it races around the Milky Way at nearly 500,000 miles per hour. Imagine if that galactic motion registered in your bones. You'd sense a gentle but inexorable drift in one direction, a slow, steady pull that never lets up. It would be like standing in the ocean and constantly feeling the tide moving under you. Entire generations would grow up with an awareness of galactic current, like sailors who can feel the wind's direction just by the way their clothes rustle. And then there's the motion of the Milky Way itself, hurtling through space at over 1,000,000 miles per hour toward the great attractor and beyond. If you could feel that, the universe would no longer seem serene or still. You'd wake each day feeling like the floor of existence itself was sliding beneath you, faster than any rocket could hope to follow. Forget morning stretches. You'd need to recalibrate your sense of direction every time you blinked. Our entire sense of balance, the vestibular system in our inner ear, would have to be completely re-engineered to handle all this chaos. Right now, those delicate fluid-filled canals in your head detect acceleration, letting you know which way is up and when you're spinning. But if they could sense constant cosmic motion, you'd be perpetually seasick. The planet's rotation alone would make you woozy. Its orbit would have you clutching the nearest wall. You'd feel the Earth spin slow slightly at night due to tidal friction, and your equilibrium would twinge in protest. Humanity might spend half its history inventing medication for planet lag. Even sleep would change. Imagine lying in bed and feeling the subtle thrum of planetary motion beneath you, the deep humming rhythm of a world spinning and orbiting through space. People might describe insomnia not as racing thoughts, but as racing universe. Poets would compare the body's restlessness to feeling the pulse of the cosmos. The idea of being grounded would take on a whole new level of irony. Travel would also get very strange. Pilots, astronauts, and drivers would have to navigate not just distances, but the sensory onslaught of layered motion. Airplanes might feel as though they're fighting invisible cosmic tides. Spacecraft would produce vertigo not from zero gravity, but from the overwhelming sensation of the universe rushing past. Imagine trying to steer a vehicle while your brain constantly screams that you're already moving in 14 directions at once. The human concept of straight line would cease to exist. But there's a silver lining. Such awareness could completely transform our understanding of the cosmos. If humans could sense these motions instinctively, we'd never grow up thinking of Earth as still. We'd feel connected to the living motion of the universe, every heartbeat synchronized with cosmic rhythm. Children would grow up knowing, not just believing, that we're part of something vast and dynamic. You wouldn't learn about the planet's rotation. You'd feel it, like the hum of an engine running beneath your feet. Our language would evolve to match this awareness. Instead of saying time flies, we might say space drifts. Instead of standing still, perhaps aligning with the planet's turn. Meditation might involve tuning out cosmic motion instead of inner noise. Philosophers would debate whether stillness even exists if every atom is always moving through space-time. In this world, motion wouldn't be something you measured. It would be something you felt, like music vibrating through your body. Of course, the price of such awareness would be constant chaos. The human brain evolved for stability. It filters out steady motion because noticing it all the time would be unbearable. You don't need to feel the earth spinning to balance your breakfast plate. Our species wouldn't have survived the evolutionary audition if we were perpetually nauseated by planetary physics. Ignorance, in this case, is a blessing of biology, but imagining it reminds us of something profound. Stillness is an illusion made for our comfort. We live in a cosmos of relentless motion, atoms jittering, planets spinning, galaxies colliding, and yet our senses create a calm pocket of perception so we can function. The silence of space, the steadiness of Earth, the tranquility of night, all of it is a beautiful lie, a trick of evolution to keep us sane while we surf eternity. So be thankful you don't feel the universe spinning under you. If you did, you might never stand still again. But remember, even if you can't sense it, you are moving. A passenger on a planet that's dancing through space faster than your mind can comprehend. The stillness you feel is just cosmic mercy, a lullaby sung by motion itself so you can sleep through the ride. We tend to think of rest as the natural state of things. A parked car is at rest. A rock lying still on the ground is at rest. You, sitting in your chair right now, feel at rest. But the universe laughs at that concept. On the grandest scales imaginable, nothing, absolutely nothing, ever stops. Stillness is a useful illusion for creatures who need to pour coffee without spilling it. But in the cosmic sense, rest doesn't exist. Everything is part of an eternal ballet of motion, from the tiniest particles to the largest clusters of galaxies, each moving in response to gravity, energy, and the invisible stretching of space itself. The first culprit is energy. Every atom in your body is vibrating with it. Even if you were frozen solid, even if the universe went dark and cold, your atoms wouldn't sit perfectly still. Quantum mechanics says that on the smallest scale, motion is unavoidable. It's called zero-point energy, a kind of eternal wiggle built into the fabric of reality. There is no such thing as absolute zero motion, because that would mean absolute nothingness. and nature refuses to play that game. Every electron, proton, and neutron dances perpetually, even when you think you're being perfectly still. Scale up, and that microscopic jitter becomes planetary motion, stellar orbits, and galactic drift. Earth spins, orbits, and moves through the galaxy. The sun swirls around the Milky Way's center. The Milky Way, in turn, races toward the great attractor, and beyond that, the local group and the superclusters are all flowing along invisible gravitational currents that stretch across billions of light years. It's like the entire cosmos is a vast ocean, and every galaxy is a wave rolling within it. You can't pause one wave without affecting the entire sea. But motion doesn't stop there. Space itself is moving, or more precisely, it's expanding. When astronomers observe distant galaxies, they find that nearly all of them are moving away from us, and the farther they are, the faster they recede. It's not that we're at the center of everything. There is no center. The universe itself is stretching, carrying galaxies along like raisins baked into an expanding loaf of bread. The raisins aren't flying through space. Space itself is growing between them. It's one of the strangest and most beautiful discoveries in science. The cosmos isn't static, it's swelling. This expansion means that motion is not something happening in the universe, it's something the universe itself is doing. Every second, more space exists than the second before. Every beam of light stretches a little longer as it travels, its wavelength pulled wider by the expanding fabric of reality. It's as if the cosmos is breathing out, slowly, endlessly. And just as you can't stop the tide from rising, you can't stop the universe from expanding. What's driving this expansion? The answer is another mystery, with an almost poetic name: dark energy. We don't know what it is, but we know what it does. It pushes galaxies apart, accelerating the universe's growth. Unlike gravity, which pulls things together, dark energy acts as a cosmic repellent, a force that keeps everything moving away from everything else. It's everywhere, invisible and uniform, like an invisible hand stretching the universe from every direction. The stars don't just move. They're being carried on a current that never ceases. This endless motion means that the universe has no fixed frame, no grand anchor to hold it still. The ancient idea of the celestial spheres, a static, perfect universe with planets fixed in crystalline shells, has long been shattered. What we have instead is a living, shifting cosmos, where every piece of matter is in constant migration. Stars are born in clouds of gas that swirl, collapse, and ignite. They burn, drift, and die, scattering their ashes into new clouds that start the cycle again. Even the atoms in your body are wanderers. The carbon in your cells was forged in the core of an ancient star that exploded long before Earth existed. That star itself once circled the galaxy before becoming dust, and that dust found its way into the nebula that became our sun. Motion isn't just out there, it's in you. If you zoomed out far enough, you'd see that the universe is like an intricate cosmic waltz. Galaxies spin and collide. Stars trace looping paths through clusters. Planets orbit in stately rhythm. Every movement is shaped by gravity's choreography, a force that's both gentle and inexorable. Over billions of years, galaxies merge, tear apart, and reform. Even the seemingly empty voids between them hum with the faint vibration of gravitational waves, ripples in space-time created by massive objects colliding. The universe, quite literally, has a pulse. And here's the humbling part. Motion doesn't just describe how the universe behaves, it defines what it is. Time itself only has meaning because of change, and change requires motion. If everything were frozen, no particles moving, no stars orbiting, no expansion stretching, the concept of time would vanish. The clock of the universe only ticks because everything is always in motion. Movement is the heartbeat of reality. It's strange to think that one day, even this ceaseless activity may fade. Billions of years from now, the stars will burn out. Galaxies will drift too far apart to see one another, and the universe will grow cold and dim. But even then, motion won't stop entirely. Particles will still twitch with quantum energy. Space will still expand, and the last photons will still drift silently through the darkness. The dance will continue, slower, quieter, but never still. So the next time someone says they're not going anywhere, remember, you are the descendant of stardust, moving through a restless universe that never sleeps. Every heartbeat, every breath, every blink happens aboard a planet spinning and soaring through an ever-expanding cosmos. Stillness is just a human comfort. The cosmos itself doesn't rest. It hums, it spins, it drifts, it breathes. And you, whether you notice or not, are part of its eternal motion.